Is chain of thought reasoning of LLMs a mirage, a data distribution lens? So in this paper, they show that LLMs or neural networks don't generalize, but I would say it's just because they overfit on training. They didn't design general enough training. But there are some valid good points to understand from this paper, mainly why neural networks and how they don't generalize if you don't create general enough training. And this is very easy for you to replicate. A lot of you ask me what kind of research you want to do. So if you go towards the end of the video, you can even skip. I explained how to replicate this research, validate it, and maybe do your own research. It's very easy. This one is easy. We already know LLMs do reason, but let's see how this actually works. How can we learn more and improve it? Introduction: the paradox of AI reasoning. Large language models, LLM, have captivated the world with their apparent ability to think through problems step by step with chain of thought prompting. When you ask an LLM to solve a complex problem and add "let's think step by step," it produces what looks like human reasoning. But is this genuine logical thinking or just clever illusion? A groundbreaking new paper from Arizona State University challenges our assumption about AI reasoning, revealing that what appears to be structured thinking might actually be a brittle mirage that vanishes when pushed beyond familiar patterns. The core question: real reasoning or pattern matching? A revealing example. Consider this simple question posed to Google Gemini. The day the US was established is in a leap year or a normal year. The model responds: the United States was established in 1776. 1776 is divisible by 4, but it's not a century year, so it's a leap year. Therefore, the day the US was established was in a normal year. For me, Flash without thinking answers leap year. But if I search Google, it says normal or non-leap year. This is crazy what they just found. And then DeepSeek says leap year and GPT-5 says leap year. Let's go back to the paper. So the model says it is divisible by 4, but then contradicts itself by saying it's a normal year. Notice the contradiction. The model correctly identifies 1776 as a leap year, then immediately concludes it's a normal year. This isn't a simple error. It reveals something fundamental about how LLMs generate reasoning. The researchers propose a radical reframing. Chain of thought reasoning is not genuine logical inference, but sophisticated pattern matching based on training data distributions. In technical terms, LLMs learn statistical regularities from their training data. They generate reasoning paths that approximate patterns seen during training. Performance degrades predictably as test queries deviate from training distributions. So as we test on things that are not in training, then performance deviates. Like this question, maybe it never saw this question. But this is maybe in the smaller models. The bigger, better models are answering this question correctly, it seems. We got some maths here, so this is formalized in maths. This equation essentially states that chain of thought performance deteriorates proportionally to how different the test data is from training data. Although it seems to me that new models like Grok 4 solving a lot of the RKGI 3, so maybe they are actually become more generally intelligent. So then they created this data alchemy environment where they can train LLMs from scratch, control exactly what patterns the models see, systematically test generalization across different dimensions. Their experiment is something anybody can do on free Google Colab. You don't need compute. You just take my LLM or my video, publish your own LLM, and you can do this research. And this is a quality research. So you train LLM from scratch and you train it on these letters, A to Z, only 26 letters. And then you have input Apple and you give it a command. For example, each letter shifted 13 points. So this is the output. Or you give it a command. This cyclic one means positions rotated right by 1. So you measure if a LLM can learn to apply this command to this input to output this. So their dictionary, it's not even meant to represent English letters. It's just 26 different symbols. And then LLM will learn what those symbols mean. And they call these atoms. And then element is just a sequence of these atoms. For example, A, B, C, D is 4 atoms in sequence, apple. But remember, this isn't the word apple, because LLM does not learn what this apple means. It is just 5 symbols in sequence that it will learn to transform. This is the key insight. The model isn't learning to predict the next word. It's just learning to apply transformation rules to this sequence. Here we can see the sequence APPL, and then the transformation, and then this control command. So there is think and answer. Think and answer tell the model what kind of output to generate. Answer token means just give me the final result. So if it sees this and the command for transformation, it should just output the final result based on whatever this transformation is, like move, shift, add, etc. So F1 is rot 13. So is it moving by 13 places? So you can have 2 transformations and answer, which means it will just rotate by 13, which is rotate by 26 in total. So it will just get back to the same letters, same symbols. But then think is show your work. So here we have 4 symbols and then 2 transformations and think, which means starting from the 4 symbols, it will first apply this F1 to the letters and then get this, and then this remains. So it will say, okay, next I'm gonna apply this and I'm gonna give the final answer, and that's the final answer. So this is easy to check if the model generated the exact chain of thought reasoning. We can just pattern match. It's easy to generate this by rules as well. So sometimes there is correct reasoning and wrong answer. So model outputs second step well and this command and answer, and then gives wrong answer, whatever it is. Sometimes there is this wrong intermediate step, but applies correct reasoning answer and then correct by accident. The output is correct by accident. So in one of the experiments, they just use this F1 transformation all the time. And they just trained on this F1 transformation, which is rotation, I think. So model learns to shift each atom, each symbol by 13 positions. And if it has 2, then shifts it twice, which returns it to original. When it sees think, output intermediate steps. When it sees answer, output the final result. So when you test the model on the training data, it works when you just give it these letters that it learned. But if you give it another function that it never saw, it's not gonna work. It doesn't know what F2 is. It only knows what F1 is because that appeared in training. Sorry, let's look at this experiment. So in this experiment, it never saw F1 and F1 together. It just saw F1 mixed with other things and F2 2 times. So it fails to apply 2 times, even though it learned everything around it. Like it learned F1, F2, F2, F1, and F2, F2. So it should know F1, F1 as well. This is something we should recreate and try again. I'm gonna maybe recreate this. Maybe, I don't know if they just trained on not enough data or this is actually like what happens. And by the way, guys, even if it is correct that it cannot generalize, I don't want you all to start saying, oh, neural networks, large language models are garbage. This is an example that we need to solve with smart design and better use of tools that are transformers and neural networks. Not just say, oh, it can be solved and that's it. And now, scenario 2, if it never saw F2, that kind of makes sense. There is no way it can know what F2 is if it never saw it. No way. Up here, at least it saw both 2 in a row and F1. So you put F1 twice in a row, it makes sense, it can maybe conclude. But if it never saw something in its life, how can it know? It's like a random thing somebody invented it without explanation and then expects this model to know. I saw F1 and its shift rotate by 13. So what is F2? I have no idea. So this is real experiment from the paper. So the first experiment I explained, training F1 and F2, F2 and F1, and 2 F2s, but never 2 F1s. So the testing is on two F1s. Model output is correctly applies F1 for the first time, but then second time it's wrong. It applies, it says here F2-like pattern. So maybe it just applied F2 one. Okay, so again, this could be overfitting, because if it just trains on this, which actually does kind of maybe prove their point. So it does seem like model is overfit on this. So maybe this could be avoided. Maybe it could learn. I'm sure it can learn in some way to apply F1. Maybe you need a more different, diverse set of data, not just these two, because this could overfit. But if you have F1 to F50, and then you just don't train like two F50s in a row or some other as well, then maybe it would actually apply properly. So this could actually show more of improper training design and not general enough, as opposed to inability of neural networks to generalize. The model was probably overfit on after F1 transformation comes F2 transformation. So it applied it here. The paper shows 3 levels of not knowing. Never seen the transformation F2 doesn't exist in training. Complete failure, completely expected. Humans. This is random invented thing. Humans wouldn't know what it is. I still don't know what F2 is. Seen the transformation, but not in this combination. Partially correct reasoning, wrong final answer. This is the most deceptive. So we can have this sneakily undercover happen in LLMs as well. The third scenario test case. So model saw F1 and F1 together and F2 and F2 together, but never saw F1 followed by F2. So it fails there as well. Probably for sure could be trained not to fail there with better design. But since language is so complex, a lot more complex than this paper tells us that there are some mistakes in training large language models that we are not aware of that could lead to these issues with them. So you see, this paper is not 100% perfect because memorizes specific sequences as a chunk because it was overtrained and overfit on these sequences. Nevertheless, this does move the field forward. This is new knowledge, and it's gonna serve as a base for other research that even you can do. If you go to my channel and search for publish your own LLM, you just ask Claude to replace the tokens with these symbols to set up the experiment like this. You need to explain to set up these functions and you can replicate this. That's it for this video, and thank you for watching and see you next time.